In this video, we will look at what happens in a nuclear reaction. We will study the different kinds of radiation and ultimately, how do you balance a nuclear reaction? Make sure you pause and fill in your follow-along notes as I go through this PowerPoint. The first thing you need to understand about nuclear reactions is that what is happening is that the nucleus changes. You also need to know that there are three types of radiation or radioactive decay: alpha particles, beta particles, and gamma rays. There's nothing you need to write on this slide, but here's what I want you to notice. Notice that the different types of radioactive decay respond to different charges. So when you shoot a radioactive substance between these plates, notice that the beta particles are attracted to the positive plate. Beta particles are negative. The alpha particles are attracted to the negative plate. Therefore, alpha particles are positive. In gamma rays, well, they don't respond. They don't have a charge. Make sure you pause and fill in this data table on your follow-along notes. This is a really great summary of each of the kinds of radiation type. So let's look at an alpha particle. An alpha particle, its notation is 4, 2, and then that is an alpha sign, and it has a mass of 4 and a positive 2 charge. You guys, it's the nucleus of a helium atom. So imagine you take away the electrons from a helium. Well, what's left? 2 protons, 2 neutrons. That's why it has a mass of 4, and that's why it has a charge of +2. Penetration into aluminum is 0.01 millimeters. What that means is alpha doesn't penetrate very well. In fact, you can stop alpha particles by holding up a piece of paper. So if you were going to be an evil villain, you wouldn't want to choose alpha particles as your weapon, because somebody is literally going to go up to you and go, no, please don't. And they'll stop it with a piece of paper. I know, right? Now there's 2 kinds of beta radiation. One is the beta electron. It doesn't have a mass, because you guys know that electrons are so small we don't really say they have a mass. Just like electrons, it does have a charge of -1, and it can penetrate into aluminum a little bit. Now look at the notation. So that funny looking B is a beta symbol. 0 at the top is the mass number, and then down below -1 because it's an electron. A beta positron, the only difference is that instead of being -1, it's a +1, and it reacts with electrons. Gamma just has that funny looking Y shape symbol. Guys, gamma is just pure energy. It doesn't have mass. It doesn't have charge. 100% energy. So what does that mean? It means the 3 kinds have different abilities to penetrate. Alpha can be stopped with a piece of paper. Beta can be stopped with foil. But gamma has to be stopped by lead. So gamma by far is the most destructive. So if you want to be an evil villain, choose gamma. Underneath your data table on your handout, there's a space to fill in more information about alpha, beta particles and gamma rays. So let's talk about alpha particles. Again, it's the nucleus of a helium atom. Get rid of the 2 electrons, all you have left is a nucleus. And all helium has are 2 protons and 2 neutrons. This is why it has a mass of 4 and a positive 2 charge. Least harmful, again, it can be stopped by paper. Beta particles, again, there's 2 kinds. They're just a small charged particle. The beta particle normally is an electron, but the positron has the same mass as an electron, which is negligible. It really doesn't have a mass, but it's a positive charge. And again, beta particles can penetrate through skin, into tissue. It can go through paper, but aluminum foil does stop it. And maybe this is why some people who belong with conspiracy theories wear the tinfoil hat. And the last kind is the gamma rays. It is nothing but pure high energy. They don't have charge. They don't have a mass. They're the most penetrating, the most devastating types of radiation. And if you look at the electromagnetic spectrum, on one end you have radio waves, and on the other end you have gamma rays, because again, they are the strongest. Balancing nuclear reactions is going to seem intimidating, but it's actually really pretty easy. There are two conditions that you must meet to balance a nuclear reaction. Number one, conservation of the mass number and conservation of the atomic number. Now, this sounds horrible, right? But it's really not that bad. Here's why. This top number is the mass number, and this bottom number is the atomic number. So on the other side, you just need to make sure that your masses add up. Sorry, guys, I can't circle very well with this pen. Do they add up to what's over here? Well, 228 plus 4 is 232. And on the bottom, these two need to add up to 90. 88 and 2 add up to 90. So check out some of these other ones. We've got 231. On the other side, you have 231 plus 0, 231. The bottom needs to add up to 90. 91 minus 1 is 90. So if you focus on these two numbers, it's actually quite easy to balance a reaction. Now, this last one's a little trickier. On the left side, you have 238 plus 4, so a total of 242. And over here, you have 239 plus, notice you have 3 neutrons. So that's going to be a total of 3. 239 plus 3 is 242. And then on the bottom, you have 92 and 2, which adds up to 94. 94 plus 0 is 94. So trust me, if you just pay attention to those two numbers and make sure they're equal on both sides, you will balance a nuclear reaction. I gave you a pretty large space in your notes to write down examples of reactions, and I recommend that you write these here. So this is an example of alpha particle emission. What does that mean? It means we are releasing an alpha particle or a helium nucleus. So if you pay attention, you've got 232 on the reactant side for the mass. On the other side, you have 228 plus 4. 232 is conserved. The atomic number is 90, and on the other side, you have 88 plus 2. It's also conserved. So again, when the nucleus emits an alpha particle, it's going to lose 2 protons and 2 neutrons. So the atomic number is going to go down by 2, and the mass is going to go down by 4. So notice how thorium has an atomic number of 90. Now it has an atomic number of 88. And how we went from a mass number 232 down to 228. So thorium became radium. And that is what is happening in a nuclear reaction. We are changing the nucleus somehow. And by changing the nucleus, we're changing the atom. Let's look at what happens when beta particle electron emission occurs. So what's happening here is you have a neutron. And when the neutron breaks down, it actually becomes a proton. And then when that happens, it releases an electron. So in your mind, if you want to think of the neutron being an electron and a proton, you can. That's not exactly accurate, but it might help you to understand what's happening. So when a neutron decays, it becomes a proton and an electron is released. It's actually way more complicated than that. You got to get into quarks and all this junk and anti-neutrinos. But if it helps you now, even though it's not correct, just think of the neutron being like a proton and an electron. And when it breaks down, you get a neutron and you also release an electron. So if you take a look at thorium, it has a mass of 231. So we need a mass on the other side of 231. Beta electron does not have mass because electrons don't have mass. So the mass number is not going to change, 231 plus 0. Here's the weird thing. So thorium had an atomic number of 90. When that neutron breaks down, it becomes a proton. So won't the atomic number go up by 1? It does. And then the math makes sense because what's 91 minus 1? 90. And if you look at this picture here, again, it's a little misleading. What it's showing is that a neutron becomes a proton and a beta particle, an electron, is released. So the neutron's not exactly a proton and an electron. It's a little bit more complicated than that. But if it helps you to think about a neutron being a proton and an electron, and when it decays, it becomes a proton and releases an electron, hey, it works. And again, in this case, the mass doesn't change, but the atomic number is actually going to go up by 1 because you're turning that neutron into a proton. So this next one's the opposite of what we just did. We're still emitting a beta particle, but this time it is a positron. So it's kind of like an electron, but it's positive. I know, weird. So when a nucleus emits a positron or a beta particle that's positive, the atomic number is actually going to go down by 1 and the mass isn't going to change. And here's why. So if you look at this reaction, are we conserving mass number and atomic number? Of course we are. 23 on one side, 23 plus 0 on the other side, 12, 11 plus 1 is 12. Well, here's what's going on. That positron does not have a mass because it's like an electron, and it does have a positive 1 charge. But here's what's really happening. You have a proton decaying into a neutron. So it's the opposite of what we just had, where a neutron was decaying into a proton. A proton is becoming a neutron, and it releases this positron. So the mass isn't going to change because both a proton and a neutron essentially have the same mass. And then the atomic number is going down by 1. By definition, atomic number is the number of protons. So you had 12, but you lost 1, so it's going to go down by 1. But again, if you just pay attention to your atomic number and your mass number and making sure they're the same on both sides, you're going to get the right answer. Now let's talk about something that doesn't happen very often. It's called an electron capture. This is where a proton and an electron will combine to form a neutron. So the mass number stays the same, but the atomic number is going to go down by 1 because you're going to take a proton out and make it into a neutron. Now the electron actually comes from one of those inner electrons really close to the nucleus, probably from the 1s orbital. And very, very few isotopes undergo this transformation. Here's an example. So you have beryllium that has a mass of 7 capturing an electron. Electrons don't have a mass, so the mass stays the same, 7. Beryllium has an atomic number of 4. It's gaining an electron, which has a -1 charge. And well, think about it. The proton is combining to make a neutron. So the atomic number is going to decrease by 1 because you're getting rid of a proton. And that is how you get lithium, because lithium has an atomic number of 3. So if I ever gave you this equation and I ended it with 7/3 and you had to fill in that element, you just look up number 3 and it's lithium. All right, the last kind of emission is gamma ray. And basically it's just the release of high energy. So the mass doesn't change, the atomic number doesn't change, the element doesn't change. You're just giving off radiation. So if you look at the picture, you have a nucleus emitting radiation, and that's about all that changes. Let's try a little quiz. Go ahead and pause the video and see if you can fill in the missing elements. I need to have a mass number, an atomic number, and the element symbol. So go ahead and pause it, try all 3, unpause it, and let's go over the explanation. So remember that mass number needs to be the same. So on number 1, you have 214 plus 4. So we need to have 218 at the top. 82 plus 2, we need to have 84 on the bottom. So 218, 84. You look up number 84 on the periodic table. Not that you can see it. And you get PO, or polonium. So the first answer should be that. Look at the next one. You need to have a mass of 234. You already have a mass of 0. So you're going to have a mass of 234. 90. What number minus 1 gets you 90? 91 minus 1 gets you 90. And you look up 91, and it's PA with some really difficult to pronounce name. I'm not even going to try it. And your answer is 234.91. Go back and look. Do you see how the mass numbers and the atomic numbers stay the same? Okay, the last one, you want to have a total of 11 for the mass because 11 plus 0 is 11. 5 plus 1 is 6. So you're going to have 11 over 6. And by now you should all know that 6 is carbon. And hopefully those were pretty easy for you. Let's take a quick look at what a nuclear bombardment reaction is. Basically, it's nuclei that get hit with something. They could be hit with another nucleus. They could be hit with a neutron, all sorts of things, okay? These typically are not spontaneous. They tend to occur artificially, meaning we humans are doing it. And we can use them to synthesize transuranium elements, other things. So here are some examples. So the first one, you see uranium getting hit by a neutron, mass of 1, charge of nothing. Here's an element getting hit by, it's an isotope of hydrogen where there's a mass of 2 instead of a mass of 1. So you have a proton and a neutron. And then the last one, you're being hit by an alpha particle. So there's different ways to do a nuclear bombardment, but it's really what it sounds like. You're bombarding the nucleus with something. Here's another opportunity for you to go ahead and try something. It says bombarding a bismuth-209 target with a beam of another nuclide produces borium-262 and a neutron. Identify the nuclide used in the bombardment. Write a balanced equation to describe this. So go ahead and pause this and see if you can fill in the missing pieces. Now, all they give you is bismuth-209. So you know the mass. Are you going to need the periodic table to find the atomic number of bismuth? Yeah. And you're adding some question. We don't know what that is yet. But on the other side, you're going to make borium-262. So you know the mass. You need to use the periodic table to find the atomic number. And you're adding a neutron. So I want you to think about how you would identify a neutron. We can just use the number n. Does it have a mass? Does it have a charge or an atomic number? Pause this. See if you can write this. Let's see. Have you gotten this far? Did you get 209.83 bismuth plus something becomes 262 over 107 borium plus a neutron? Did you get that so far? Perfect. Now you should be able to look at your atomic masses, your mass numbers and your atomic numbers and figure out what is missing on X. I'll go ahead and let you try that, okay? So this is what we have. You should first look at the mass number. And you're going to notice that you have 209 plus some number equals 263. So when you subtract 209, you get, and by the way, A is the mass number, a mass number of 54. Then you want to do the same thing for the atomic number. And don't ask me why they use Z for atomic number. They just do, okay? 83 plus Z equals 107. Subtract 83 from both sides, and you get Z is 24. Go look up atomic number 24, and guess what? It's chromium. And that is what you're bombarding that with to create that reaction. Now, I've already given you this chart in your notes, so you don't need to write anything down. You just need to understand what it's telling you. The question is, how can you predict what kind of decay will occur? So notice the first column is the reason for instability. If you have an element with excessive mass, it's probably going to decay by alpha decay. You're going to release an alpha particle that's losing 2 protons and 2 neutrons. And it says the change to the N to Z ratio, that's the number of neutrons to protons, okay? The next reason is that your N to Z ratio is too high. That is, your number of neutrons to number of protons is too high. What's going to happen is beta decay, where a neutron changes into a proton and an electron. And think about it. If your N to Z is too high, you have too many neutrons. Doesn't it make sense that you would want to turn a neutron into a proton? What if the N to Z is too low? Well, now you have too many protons, right? So if you do a positron emission, you're turning a proton into a neutron and a positron. But again, you're reducing that number of protons. You're trying to always get back to an N to Z ratio of 1. That is, neutrons to protons is 1. Another possibility when N to Z is too low because you have too many protons. Guys, remember, when you have a numerator and a denominator, and that denominator becomes really big, your overall answer becomes small. We saw this with the K expressions, equilibrium, Ka, the acid dissociation constant. So another opportunity here to fix the situation is to capture an electron, because a proton and an inner shell electron will become a neutron. So now you're going to raise that numerator a little bit to balance out that ratio. And then, of course, there's just an energetically excited nucleus. So that has nothing to do with the number of neutrons or protons. And this is going to be gamma emission or a gamma ray. It's going to lose some energy. Now, there's a really great PhET simulation. I can't think of the name of it off the top of my head, but it has to do with this. And if you go in there, it has you build atoms, and you actually can see what causes that nucleus to become unstable. When the nucleus is stable, it doesn't move. But when it's unstable, it starts to kind of shiggle, that's a new word, wiggle back and forth, shake, okay? Shake and wiggle, we'll call it shiggle. It really gives you an idea of that neutron to proton ratio, okay? So it's just something if you want to go and look it up. Warning, I'm a nerd and I love this. This is called a radioactive decay series. Typically, this happens with really heavy elements, and it goes through a series of decays, both alpha and beta. And if you take a look at the graph, you have atomic number on the x-axis, and over there on the y, if you turn your head, it says mass number. So if you look at this very first right here, this arrow here, you go from uranium to thorium. Look at the graph. What changed? Number one, the mass went down by 4. It looks like it goes from 238 to 234. And the atomic number dropped by 2. What kind of radioactive decay causes the mass to go down by 4 and the atomic number to go down by 2? Alpha decay. So every time you see a slanted, sloped line, that's alpha decay. Now look at this flat piece right here, okay? That is a beta decay, because look what's going on. Thorium increases in atomic number, but the mass didn't change. And then it changed one more time. It went from, sorry, you guys, I wrote on it, I can't read, Pa to uranium, it looks like. Again, beta. So when it's flat, it's beta, because the mass isn't changing, but the atomic number is. And then you'll notice this very, very long line of alpha decay. And then another series of beta followed by alpha, beta followed by alpha. So eventually uranium becomes lead, it looks like. And it took a lot of transitions. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 radioactive decays. Isn't that cool? You can't talk about radioactive decay without talking about half-life. Half-life is the time required for half of a sample to decay into a different isotope. And I don't think we're going to do very much of this math, but we do if you take Chem 1000. And you guys, it's really pretty easy. Like, let's say you start with 200 grams of something and its half-life is 5 minutes. In 5 minutes, you have 100 left. In 5 more minutes, you have 50. In another 5 minutes, you have, what's half of 50? 25. In another 5 minutes, you have half of 25 or 12 and a half. And you just keep doing that until however much time is up. But the shorter the half-life, the more intense the radiation that it emits. Lots of reasons we would want half-life. We can use it to date rocks. Okay, not literally date rocks, but to figure out the age of rocks. And there's other medical applications to this. Let's look at an example of half-life. Gold 128 undergoes beta decay to yield mercury 128. Did you need to know that? No. The half-life is 2.7 days. What percentage is left after 8.1 days? Well, we assume that at time zero, we have 100%. At one half-life, we are at 2.7 days. 100 gets cut in half to 50. Another half-life goes by, so 2.7 days becomes 5.4. We had 50%. Half of that is now 25%. Another half-life goes by. So now we are at 8.1 days, and that 25% goes down to 12.5%. So at time zero, we had 100%, okay? And then that became, so first half-life goes to 50%, second half-life goes to 25%, and the next half-life goes to 12.5%. So we go down to 50, down to 25, down to 12.5. You just keep going by half until you get to your time. Just make sure you start at time zero. If listening to me was a little bit difficult to follow, go ahead and take a look at how they showed it. There's 3 half-lives. So again, the initial amount is 100%. After one half-life, you go down to 50%. After another half-life, 25%. Another half-life, 12.5%. There are so many applications to nuclear reactions. I mean, obviously, nuclear power would be a great one. But let's talk about the medical applications of isotopes. We can use isotopes or radioactive decay to power generators, like pacemakers. We use it to diagnose things. You can inject somebody with radioactive nuclides and you look for certain substances to see what's going on. For example, a really good one would be to locate tumors. They actually inject you with radioactive sugar and they look to see where the sugar goes. You all, cancer loves sugar. So if there's a bunch of this radioactive sugar going to a particular place, you probably have a tumor there. Just a little FYI, cancer cells, number 1, will feed on sugar. Cancer cells, number 2, will feed on an amino acid. I believe it's glutamine. I could be wrong. And the third thing is they'll cannibalize each other. So if you're prone to getting cancer or you've discovered you have cancer, cut sugar out of your diet. You're cutting off its supply. Cut off eating sugar, cut off anything that will break down into sugar. And the last one is a PET scan. It also can detect abnormalities within your body without disrupting the tissue. And again, it uses radioactive dye. Radiation is so weird. Enough radiation in the right amount in the right place can cure cancer, but too much radiation can cause cancer. I mean, how strange is that? So there are 4 results of biological effects of radiation, okay? Number 1, radiation can pass right through a cell, no damage, everything's fine. Second case, the cell is damaged, but it can fix the damage. Yeah. Third one, the cell is so damaged, it can't be repaired. And now that cell is just abnormal, okay? And if that cell is able to proliferate, meaning if that cell is able to go through the cell cycle and make new cells, you are now making damaged cells. Not a good thing. And the last situation is that the damage is so severe, it causes cell death. So we go no damage, damage but can be repaired, damage not repairable, but the cell survives, so damaged it dies. No damage, damage that can be repaired, damage that can't be repaired but can be passed on, death. Those are the 4 effects of biological radiation. Besides medical technology using nuclear reactions, perhaps the most well-known application is nuclear energy, nuclear reactors. In nuclear reactors, fission is occurring. Now, fission is the splitting of a heavy nucleus into 2 or more lighter nuclei. And fusion, we're going to talk about in a minute, is fusing. So if you use your hands, you can remember fission versus fusion. Fission, fusion. Fission, splitting, fusions, fusing together. You're probably going to hear a lot of talk about creating nuclear reactors, different kinds of nuclear reactors, mobile nuclear reactors, because as we build data centers in artificial intelligence, they require tremendous amounts of energy to run on. I recently read that one ChatGPT query, one, is the equivalent amount of energy of 10 Google searches. So AI requires a lot of energy. But here are some examples of nuclear energy reaction. So the first one, a uranium-235 atom can be bombarded with a neutron. And when that happens, here's what's really cool. Look at the very last product. It can create 3 neutrons. So 1 neutron will release 3 more. Those 3 go and hit a uranium-235, and 3 more each get released. So I don't know if you could see how easily or how fast this is exponentially going to increase neutrons. And there is a danger to nuclear energy because a reaction can go out of control very quickly because one bombardment releases 3 neutrons. Then those 3 each release 3, we're up to 9, and each of those release 3, and then the math gets ugly. But there are ways to control that. And here in the United States, we build reactors very safely so that we can control the amount of neutrons available. We can control the heat, all sorts of cool things. For those of you who've heard of Chernobyl back in 1986, it's now in the Ukraine, but it used to be part of the Soviet Union. There was an unauthorized experiment, and they dropped 5 of the 6 safety factors, and that allowed the reaction to grow out of control. But anyway, those are just some other examples of fission reactions. This is just a picture of how a nuclear power plant works and roughly what's going on. You've got the rods that can control the neutrons. You do have to have a cooling system, which is typically water. In Kemmerer, Wyoming, they're building a natrium reactor, and it's a new experimental kind of reactor. It sounds like it's going to work really well. I guess we'll find out. Now, fusion is the exact opposite of fission. Instead of splitting, you're fusing. And this is where you take small, light nuclei and form heavier nuclei. Guys, this is what happens in the sun and stars. So like in our sun, hydrogen atoms are combining to make helium, and then helium combines to make other heavier things. And in stars, you can keep making more and more elements. At some point, though, in the formation of a star, once iron starts to be formed, the star will tend to collapse on itself. It gets into the weeds here with energy and stuff. But fusion reactions are not practical yet on Earth. Number one, we really can't control them very well. The infrastructure, like the amount of pressure and heat it takes to happen, we're not quite there, but we're getting there, and we're really close. I have a feeling that maybe in your lifetime we might even see some fusion reactions. This is just a picture of a fusion reactor. Again, we're trying to make it happen. I know we're getting really close. And you guys, if we can make a fusion reactor, it'll change the world. It will produce so much energy without like the nasty radioactive decay that we get out of our nuclear reactors. It truly will change the world. But by the way, there's been a lot of research in previous years where, like right now, you take that nuclear that radioactive nuclear waste from a reactor and you've got to store it in the heart of a mountain somewhere, we're actually finding ways to take that waste and continue to process it and get more energy out of it. So there's a lot of really cool technologies on the horizon. I think you're going to see a push for nuclear energy. It's not a renewable like wind or solar, but it's almost renewable. It's really relatively clean with the exception of a little bit of radioactive waste, but now we're finding ways to use that. And gosh, we can just create so much energy from a nuclear reactor. If we can get fusion reactors off the ground, it's going to change the world. What an exciting time to be alive.